Does the mic sound okay if I wear it like this? Good? Fantastic. All right. Can you hear me in the back? Yes? Great. All right, then let's get started. So today we're talking about logistic regression. Actually, we already started talking about logistic regression last time, but today we're going to go into quite a bit more detail. I haven't fully figured out these technical difficulties that we're seeing. So what we're going to do for the near future is just cross our fingers. But maybe later on in the semester we'll have a better system. But for now, please bear with me if these things do happen. Okay, but anyway, what is today's lecture about? So, not yesterday. On Monday, we started talking about classification, as well as these different ways that we can think about classification or probabilistic models for classification, these discriminative versus generative models. And we talked about things like linear discriminant analysis as an example of a generative probabilistic model, and logistic regression as a discriminative probabilistic model for classification. So today what we're going to do is we're going to focus in on logistic regression and derive it out in detail and see what sort of the internals actually look like, what it actually looks like under the hood. And this is going to also kickstart our discussion into what we call iterative optimization, because problems like logistic regression and the vast majority of problems, machine learning problems that you're going to see in life, have no analytical solution. Like there's no set the gradient equal to 0 and then read off what theta should be kind of solution like we saw for things like least squares linear regression. Most of the time, that's not going to be the case. We're not going to be able to do that. Instead, what we're going to have to do is rely on what we call iterative optimization techniques in order to find a good solution. And we're going to start our discussion of that today as well. But let's do a little bit of a quick recap from last lecture. Remember, what we're focusing on, at least for now, just to make things a little bit more concrete, is binary classification, right? Where what did we have before? Well, before in regression, we had, our targets y could be like any of these real values that we wanted to predict, right? Now, when we focus on classification, our targets y, we call them labels, only can take on a certain number of discrete values. We say like if it's like k, then it's, takes on values either 0, 1, 2, all the way up to k minus 1, right? And in particular, for binary classification, k equals 2. So our labels can only be 0 or 1. We're just trying to separate class 0 from class 1. That's what we're doing here. And we posited that we have this linear model, right? So we're still working with linear models just to make things nice and simple. This linear model was pretty nice before when we were doing linear regression, right? Because our targets were real values. But it's a little bit of an awkward fit for classification in general, right? Because this outputs some unconstrained real number. How do we actually take that and then use that to make a decision? Are we going to predict 0 or are we going to predict 1? Well, it's not immediately clear what we might do when what we have is a real number that we're working with, right? So what do we propose? We propose that we treat the whole thing probabilistically, right? We transform this output, theta transpose x, into a number between 0 and 1. And then we're going to use this to represent the predicted probability of class 1. And we did so using the sigmoid function, which looks like this, right? It takes in any real number from negative infinity to infinity, and then it squashes that into the range between 0 and 1, so that we can essentially treat that as a probability value, right? And then we basically said the sigmoid of our model output, right? We're going to treat that as the probability of the predicted probability of class 1 given my input x. And then consequently, we have the predicted probability of class 0 is just 1 minus that, because we know that probabilities have to sum to 1, and there's only 2 classes that we're working with. Right? So just a quick recap from last time. This is the setup for logistic regression, right? This is how we're defining our model. Okay? And then we did a little bit of work last time to start working on what's the maximum likelihood estimate of theta. I'm going to do a little bit of recap of like the end of what we did last time, but then we're going to try to expand on that to see if we can try to figure out what's our solution actually going to look like. We didn't really get that far last time, right? I just left it somewhere and then said, well, you'll see more of this next time, and you'll see more of this in discussion. You will see more of it in discussion, but we're going to work out a little bit of what it looks like and do some algebraic manipulation to see if we can get somewhere kind of interesting. So pray with me. Let's see if this works. Okay. So remember we have, the MLE. And last time we started from a product of probabilities. This time I'm directly going to start from the sum of log probabilities, okay, just to make things a little easier to work with. So the sum, right, of what did we have last time? We have 1 minus yi, log probability of 0 given xi, plus yi log probability, or predicted log probability of 1 given xi. Right, and remember we worked out like how to actually, derive out this expression, but also if you look at it, it kind of makes a lot of sense, right? Because, well, what is yi? Yi is either 1 or 0, right? Those are the only 2 values that it can take on. So what if yi is 0? If yi is 0, then this whole term is 0, right? And then what I'm left with is 1 times the log probability of 0, which is great, right? Because that's the label that I have for that class, or for that data point, I. Right? And what happens if yi is 1? If it's 1, then this whole thing is 0, right? Because we have 1 minus 0. And then we have 1 times the log probability of 1 given xi. And so all of that kind of checks out in the way that we expect it to, right? So this is perfect. We have a sum of log probabilities of our data points. Cool, so let's actually write this out, right? So remember, we worked out what these log p thetas actually look like, right? Because we know what they are. They're like the sigmoid of this linear function, right? And they look like this. Let's write it out in a bit more detail. Minus yi. And then what is log p0 given xi? It's something that looks like negative log of this whole thing, exp theta transpose xi plus 1, right? We get that thing first. And then I'll start on the next line because I'm running out of space. We have yi times what is log p1 of, log p of 1 given xi. Well, we have our numerator is theta transpose xi, right? Minus kind of like the same denominator term, right? Exp theta transpose xi plus 1. Okay, this is what we have. Now, if we stare at this long enough, you don't even actually have to stare at it for that long, but you're going to be able to see that there's actually something here that can simplify this. And what can simplify this is I have yi times negative log of this thing, but then over here I have negative yi times the same thing, Okay, so those two terms are going to cancel, right? Because I have plus and minus of the same thing. It's like yi times the big log expression, right? So those things are going to go away, and then the only terms I'm going to be left with are the following. I have, let's write this term first, because it's a positive term. Yi theta transpose xi. And then what's the other term that I have? It's 1, right, times this thing. Minus log and then I claim that all the other terms that you would have, they all just cancel out. Okay, minus yi times log of that thing plus yi times log of that thing, those things just go away. And so this, with some algebraic manipulation, is what we end up getting to as the MLE that we're trying to solve, the MLE problem that we're trying to solve. Okay? Okay, so that's cool. So here it is again, right? I just wrote it out. So we have this problem, right? Argmax of the sum over all of these terms, right? So let's try to actually take the gradient of this thing. Okay, what is the gradient of this thing with respect to theta? Well, I move my gradient inside the sum, right? So I have a sum of individual gradient terms. What's the gradient with respect to theta of this thing? Yi is a scalar, right? So yi can stay out in front. That's no problem. And then the gradient of this thing with respect to theta, right, if you remember your rules, it's actually just xi, right? There's like a linear relationship between theta and xi. So the first term, I get yi xi. Okay? This looks a little bit more complicated, but it's not super complicated either. All I really have to do is try to apply the chain rule as many times as possible in order to try and get to what the answer is, right? So if I apply the chain rule, basically what I'm saying is I'm going to take the gradient, right, with respect to log of this term, and the gradient of log of this term with respect to the whole thing on the inside, right? Well, what's the derivative of log x? It's 1 over x, right? Or 1 over whatever it is that you're differentiating with respect to. So the first term that I'm going to get, right, when I apply my chain rule, is the denominator, right, where I have this whole thing on the denominator, right? And then I have to apply the chain rule and figure out, well, what's the actual, derivative or gradient of the thing on the inside with respect to theta? Well, this 1 goes away, right? That's got nothing to do with anything. But then I have to apply the chain rule again, right? Because I have exp of a term involving theta. So I take the gradient of exp of this thing with respect to the whole thing on the inside, right? And what's the gradient, or what's the derivative of e to the x? It's e to the x, right? So then I get this term that pops out. And then finally I'm on the inside and I say, well, what's the gradient? What's the gradient of this thing, theta transpose xi with respect to theta? We already worked that out. It's just xi. Oh, no. Still got it. Okay? So then that's what the gradient becomes. Does this term look familiar to anyone? Yeah. Oh, no. Yes. Oh, yeah, it doesn't just kind of look like the sigmoid. It is the sigmoid, right? So miraculously, we got a sigmoid out of our gradient somehow. But yes, I can rewrite this, right, as yi minus sigmoid theta transpose xi times xi. I just put two terms inside of parentheses, right, and then you would distribute to get the thing on the previous slide, or on the previous line. Cool, that's kind of neat, right? I claim that it's actually not super complicated to take this and write it in matrix vector form. I'm going to do it without too much of an explanation. But if it's confusing, it's also a good exercise to try to figure out, or to try to get a little bit more comfortable with how to take these sums and then turn them into matrices and vectors. That's a good exercise, right? But in matrix vector form, this gradient looks something like x transpose y minus s theta, something I'm going to call s theta. I'll explain what that is in a second. But let's first take a look at the terms that we already know. X, right? Not x transpose. What is X? It's our design matrix, right? The thing where every single row is one of our data points, right? The ith row is our ith data point xi, right? Y. Y is no longer a single number. This y represents a vector, right? It's an n-dimensional vector where n is the number of data points, and then the nth entry in that vector is our the ith entry in that vector is our ith label, right? We know what those things are, x and y. We've seen those before. This s theta is new. This is just a notational convenience. What I mean by this is the vector that looks like sigmoid theta transpose x1 is the first entry, right? And then we go all the way down to sigmoid theta transpose xn as our last entry. Okay, so then this becomes what our gradient looks like. So this is the thing that if we could, we would really want to set this thing equal to 0 and then figure out what theta should be. But as it turns out, as we'll see on the next slide, that's actually a little bit hard. Anything unclear up to this point? Yes? Sure, yeah. So how do I go from the summation into this matrix vector form? I know this is not exactly going to help that much, but it is a little easier to go from matrix vector form to summations, right? Like you can sort of write out what this matrix multiplication actually is. And I know that that's not, like an answer that you can necessarily programmatically follow, but that's kind of the way that you build up the intuition for how these things kind of relate to each other. So the things that I do are, when I'm looking at a summation, and I think I could probably write this in matrix vector form, I try something, and then I see whether or not that sort of corresponds to the right thing. And I don't try anything. I also do like this dimension matching, right, to make sure that things actually check out in the way that I want my dimensions to be. For example, grad theta. I know grad theta is a d-dimensional vector, right, where d is like the dimension of x, right, because theta has the same dimension when we're doing these linear things, right? So I know that this thing is d-dimensional, is a d-dimensional vector, so I know I want this thing to be a d-dimensional vector, right? That kind of makes sense then if I do x transpose, because x was n by d, now it's d by n, right? So it's just like a lot of dimension matching and then pattern matching in your head to figure out how to get there. A mathematician would tell you that's a terrible answer, but for our purposes, it's going to be good enough. Let's pause and think for a second about what it is that we've just done. Okay, so we have this MLE that we're trying to solve, and we just found our gradient. That seems like a great first step, right? If we could find an analytical solution for logistic regression, how would we do it? Well, we'd probably do it the exact same way that we found all of our previous analytical solutions, right? We would take our gradient, which is this thing, right? X transpose times, y minus s theta, and set it equal to 0, and then try to solve for theta. You're welcome to try to do this if you want. If you manage to do it, let me know, and then we can probably publish something on that, because I don't think it's actually going to be possible. So if it is possible, that's really cool. But it's probably not possible, so instead what we do normally when we're trying to solve logistic regression is we use something called iterative optimization. Specifically, we're going to use a technique called gradient descent, or gradient-based optimization, in order to try to get at our answer, our theta that we think is the best one, okay? We're going to do that in a sec, but before that, I think it's kind of interesting to actually look at what we've just done and then try to analyze what it is that we're trying to find. What is the desired solution for this problem that we've just defined, okay? So characterizing the solution to logistic regression. So at least for MLE, right, the theta that I would find from MLE, or the theta that I hope to find from MLE for logistic regression, satisfies that the gradient is equal to 0. That would be the definition of the solution, right? It would need to have, it would need to be some theta that when I evaluate this gradient, I get it equal to 0. But we can ask the question, when does that actually happen? So when is it the case that x transpose y minus s theta is equal to 0? Yes. So that is part of this. That is part of the answer. Yes. So it has to correctly classify every single point. We haven't really defined exactly what classifying the points mean, but yes, that's definitely on the right track. Yes. So yes, that is the that is the general linear algebra answer that we need. We need y minus s theta to sort of be in the, I guess, the null space of x transpose, or the left null space of x. That is correct. Can someone elaborate on that maybe a little bit, or give your own answer? That's okay too.
So I was going off what that person said. I think all of our y values need to fall in a sigmoid shape curve for y minus.
All of our y values need to fall in the sigmoid shape curve. Well, actually, that's a really good point, right? So all of our y values, what are the y values? Like, what are the entries inside our vector y? They're only zeros and ones, right? And we can't change those, right? That's just like the data that we're given. Those are the labels that were provided, right? So unfortunately, the only thing that we're going to be able to control is s theta. Everything else is kind of fixed. Let's say, okay, so building on this answer, right, where we want y minus s theta to be in the null space of x, okay? Suppose that, similar to the assumption that I made for like least squares linear regression, for example. Suppose that my x is full rank, okay? So I don't have any features that are, kind of redundant or like a linear combination of some other set of features. Okay, can anyone say in that case what I would need to satisfy in order for this to be, for this gradient to be 0? I guess this is a linear algebra pop quiz. So if x is full rank, right, then what is the only vector v such that x transpose v is 0? Yes. 0. Yes. Okay. So assuming that my x is full rank, actually this gradient will be 0 if and only if s theta is equal to y. Okay. That's the only time I'm going to have this gradient equal to 0. Okay. What does this mean? Well, what this means is that for all of my data points, right, my predicted probability of, well, I guess the way that I wrote it is a little bit confusing, but basically my predicted probability of class 1 is equal to whether or not that class was actually 1. Okay, so if the class was 1, then I'm predicting probability 1 that it's 1. If the class was 0, I'm predicting probability 0 that that class was 1. In other words, I am completely confident, my classifier is completely confident in every single correct answer, right? So we can't change our y's, they're all zeros or ones, but we can change our s theta, right? And basically what we're saying is we want these s thetas to kind of drive in the correct direction as far as possible, right? We kind of want the theta transpose x's to be like either negative infinity or infinity, so that what comes out of the sigmoid is either 0 or 1. And whether it's 0 or 1 depends on what the true label is. Okay, but well, actually, did I give away this answer a little bit? When does the predicted probability from this model, when does that equal 1 or 0? Think about what the model is, and think about the sigmoid function. Yes?
Doesn't the sigmoid function approach 1 and
Yeah, exactly. So it approaches 1 when the input's infinity, and it approaches 0 when the input's negative infinity, right? So for this to actually happen, we would need theta transpose x to be, well, I wrote equals here because I'm sloppy, but, approaching infinity or negative infinity, right? And for x that have, finite entries, which we would assume that our data points have finite entries, it'd be really weird if it didn't, right? This is really only going to happen when we have the magnitude, the norm of my parameters growing unboundedly, right? So my entries and my parameters have to get bigger and bigger and bigger in order to have the sigmoid values be closer and closer to 0 or 1, and that's the only way that I'm actually going to be able to find, quote unquote, the optimal solution, or the MLE, for this particular problem. We can intuitively think of this as sort of the slope between 0 and 1 getting infinitely what we call steep. So it's 0, and then it just jumps up to 1. And those are kind of like the only two values that we even consider, right? We don't consider any data points having probability 0.8 or 0.2 or 0.5 or anything, right? It's only 0 or 1. That's all it is that we're doing here. But remember, we've already kind of talked about, well, this seems a little bit nasty, right? Because, if we run this, right, it seems like all we're going to be doing is trying to make our theta bigger and bigger and bigger forever. And this also relates back to kind of some of these issues that we've talked about previously, right? Where like, it doesn't actually seem like a good idea in the first place to try to make those entries in theta so big, right? And that's what we were talking about when we were talking about map estimation. And so there's a similar solution here. Basically, there's the same solution here, right, where we don't want our theta to, grow unboundedly. And so what we're going to do is we're going to add regularization to the problem. Another way to say it is that we're not going to do MLE. Instead, we're going to do map, okay, map estimation. And typically, what people do with logistic regression is they'll take the MLE problem that we had before, and they'll add an L2 regularization term, just like we did with, for example, going from least squares linear regression to ridge regression, right? So we'll add like a lambda and then 2 norm squared of theta. And then that'll be an additional term in our loss function, which will kind of prevent this bad behavior because we'll have an extra term in our gradient. And then setting that equal to 0 will not, characterize this solution that we don't actually want. Yes? Yes, so I'm glossing over this because you'll see it in more detail on, I think, probably the next homework. But yeah, the basic idea is add an L2 regularization term to logistic regression so that we don't have this silly problem. Yeah, so I guess it's not this point right here about getting infinitely steep. I'm not really defining steep with respect to what. We can sort of think of it as like steep with respect to changes in x. Okay, so if my theta is really large, right? What did we say before about like our intuition behind smooth functions and things like that, right? When my theta is really large, then even small changes in x can result in large changes to theta transpose x, right? And if, for example, that jumps me from some large negative value to some large positive value, then I'm going to be essentially jumping from 0 to 1 very quickly in terms of the probabilities that I'm predicting, right? Compared to if my theta is small, there's a more gradual change where I can, express probabilities in between 0 and 1 as well. Yes? What problem are you trying to avoid again by using regularization? So we're trying to avoid this problem where there's this weird property of the MLE solution, which is that theta should have infinite magnitude. It's the theta with infinite magnitude that's actually the minimizer of this loss function or the MLE, whichever one you prefer. And that's going to be weird, right? Because we can actually never reach that solution, so we're going to be chasing that solution forever. And we don't want that solution in the first place because of problems like overfitting and things like that, which we'll talk a little bit more in detail about in the coming weeks. Yes? So if you don't have the regularizer, the MLE version of this would never work. Yeah, basically, you could run, so I'll talk about iterative optimization next, and basically what we can think about is like we're iterating, right? And technically, this iteration should never stop, right? Because we can always continue to find better and better theta just with larger and larger magnitude entries, right? Practically speaking, we could cut it off at some point and then say like, well, this theta is not exactly the MLE, but it's pretty close and it's pretty good. So technically, you could do something like that. But theoretically speaking, you'd essentially never stop. You'd be trying to find larger and larger theta, which look better and better under this, this MLE maximization problem. That's correct, yeah. So as your theta gets bigger and bigger, right, what's happening is that we get closer and closer to assigning either 0 or 1 probability to every data point that we have, right? Which, at least from the perspective of MLE, just looks better and better the closer you can get to 0 or 1, right? You never actually get exactly to 0 or 1 unless you have like finite precision like a computer does, right? But in theory, you would be approaching 0 or 1 forever. Okay, you'll see more of that on your homework, I believe. For now, let's turn tail and go back and start talking about iterative optimization, which is going to be the way that we actually find solutions to problems like logistic regression. Okay, so here's a statement that's basically always true. For problems where we cannot find an analytical solution, like set the gradient equal to 0, we're basically always going to rely on iterative optimization in order to find good parameters. Okay, that statement is general enough that it's basically always true. And basically, at a high level, what iterative optimization is we start from some initial, what we call guess, right? So we have some theta that we start with. It might be good, it might be bad, who knows? But what we do is we try to continually refine that guess of theta. So we start from some theta, and then we try to refine that into a theta that's better, right, according to our objective. And we continually do that until we're satisfied with our final answer. So remember, we might never be satisfied, right? Like we might always be chasing some maximum that we can never achieve if we were trying to go to infinity, right? But that's why we say like until we're satisfied, because maybe we stop before that, just based on some time that we're willing to spend trying to solve the problem, or different things, different practical things along those lines, right? So this is a very, very high-level sketch of what iterative optimization looks like. By far, the most commonly used set of iterative optimization techniques is what's known as gradient-based optimization, or specifically first-order gradient-based optimization, which basically means we're using first-order information, like derivative information, gradient information, right? We're not using any like second-order information like Hessians or something like that, right? And there's like variants on how we actually do this gradient-based optimization, but the general formula is extremely simple. It's basically you repeat this following step forever, or until you're satisfied, or until you run out of patience. Let's actually look at this in a little detail because it's important. Okay, I'm switching to loss functions, all right, because that's how we're going to characterize most of our problems. Okay, so loss function, remember, could be like negative log likelihood, which is the argmin that corresponds to the argmax that is MLE, right? Something like that. So I'm looking at here the sum of all my losses, and I divide by n to make things a little bit nicer, but that doesn't change the problem, right? It's just something that makes things on a little bit of a better scale. So I look at my average loss, and then I compute the gradient with respect to my parameters of the average loss, okay? And then what I'm going to do is I'm going to take my parameters and I'm going to move them in the direction of this negative gradient, okay? What is this alpha? This alpha is some small number, okay? Think like 0.01 or like 0.001. It kind of depends on what it is that you're working on, but it's some small number that we usually call like a step size or a learning rate. And it basically says don't move too much in that direction, right? The gradient's only an approximation. It's a local linear approximation that's going to be good locally, but we don't want to trust it too far out, right? So in order to not trust it too far out, we're only going to move sort of a little bit in that direction that the negative gradient is telling us. And then once we do that, we assign that to be our new parameters. This left arrow here means assign, right? So basically, we have this whole thing on the right-hand side. We do that first. We take our parameters, and we move them a little bit, right, in the direction of the negative gradient. And then we assign that to be our new parameters. And then we just repeat this update step over and over and over again until we feel like we found the theta that's actually the optimum or close enough that we're satisfied. So, yes? What is a good choice for the initialization? That's a great question. So that depends a lot on the particular problem, and or it depends a lot on the particular model. So for example, for neural networks, which we haven't talked about, but we will talk about them later, there are certain schemes or techniques that we can use to try to initialize the parameters such that it's easy to optimize them. For logistic regression, it doesn't actually matter, because one thing that we won't really talk about, but the logistic regression problem is convex. So we can basically initialize the parameters from anywhere, and then we'll get a good solution, or kind of the globally optimal solution, as long as we run it for a while, right? So there are still initializations that are better. For example, if I could figure out how to initialize from the optimum, right, then I would converge in 0 steps because I'm already done, right? But in general, for these types of easy problems, we don't really care too much exactly where you initialize from. You can initialize like all zeros as your theta or whatever you want, right? Random values, right? And then from anywhere, you should be able to converge to the global optimum. Okay, so this is gradient-based optimization in one line, right? I claim it's basically just repeating this equation, this update, over and over and over again in order to continually make your theta better. And then eventually you'll reach the theta that's the best, or you'll be happy enough with your theta, or you won't be happy, something went wrong, and then we have to adjust. But usually this will work out just fine. You might be wondering, why is it going to work out just fine? What's the intuition behind this? What the heck is even going on? Those are questions for next time when we talk a little bit more about optimization or specifically gradient descent. But we will go into a little bit of intuition right now. But just know that if it doesn't make complete sense after today, come back on Friday, and then hopefully it'll make a little bit more sense then as well. So the gradient is basically telling us how my loss value changes if I make small changes to my parameters, right? It's like we said, it's a local linear approximation, right? So it's using a linear function to approximate, well, if I move my parameters in this direction, right, what happens to my loss value? In that direction, what happens to my loss value, et cetera, et cetera. And this is not necessarily an obvious statement. We'll try to build some intuition about this next time. But this following statement is true. We decrease the loss if we move with a small enough step size, with a small enough alpha, along the direction of the negative gradient. And the kind of the way to think about this is we're sort of going opposite the slope in every dimension because we could have multiple dimensions of theta, right? So essentially, if it's a loss function that we're trying to minimize, going in that negative gradient direction, sort of moving downhill, if you will, is going to bring us closer and closer to this minimum that we're trying to find, right? The opposite is true if we're doing a maximization. Like if we're doing MLE in its native form, we would be doing gradient ascent, right, where we're trying to sort of climb that hill towards the global maximum. But like we said in machine learning, we're basically always going to be thinking about minimization problems. And so gradient descent is typically the thing that you're going to hear a lot when we're trying to solve these problems. And gradient descent is this. It's literally just this, right? It's repeatedly performing this update step, which we already wrote on the last slide, right? We just do this over and over and over and over again. And hopefully, if our problem is well structured, like for example, logistic regression, and we have a small enough alpha, which is a hyperparameter, right? It's something that we have to set ourselves. Then eventually we're going to get to the setting of theta that's good. That's sort of like the optimum of the problem that we're trying to solve. So let's actually circle back for a second and think about how this relates to this thing that we were just talking about with MLE of logistic regression, right? So when it came to logistic regression and MLE, we found our gradient, right? And so we would be able to sort of take gradient steps along the solution. But remember what we said was that the optimum for that MLE formulation actually has the magnitude of theta being infinite, right? That's what actually minimizes this loss function that I had before, this negative log likelihood loss function or the MLE maximization, whichever one you prefer, right? And so what that means from the perspective of iterative optimization or gradient descent is that essentially I could take gradient steps forever, right? I could take an infinite number of gradient steps when I'm doing the logistic regression MLE formulation, and I would continue to get better or better in terms of the loss, right? Every time I took a step, right? And so that's why we need things like either regularization or we just sort of like terminate at some point because we don't want to wait forever, right? And that's kind of the practical bits behind how we're actually going to be looking at the logistic regression problem and how we actually solve it. So for convex problems, like, they should probably say like logistic regression with L2 regularization. For convex problems like logistic regression but regularized and with the right step size, the right alpha, we can show that we will find the parameters that minimize the loss. And so that globally minimize the loss, and that's kind of nice. Okay, it's not going to be true for all the problems that we're going to look at, but at least for some of these simple problems, that does hold. Yes?
Is there any limitations to alpha being like scalars, maybe like a matrix or something?
Oh, good question. So can alpha be something higher dimensional, like a vector instead of a scalar? Yes, actually. So what that amounts to is you can imagine, for example, alpha being a vector of dimension d, just like theta, right? And then you could basically be saying, I'm going to take different size steps in every single dimension of my parameters. Why would I do something like that? Well, maybe I know something about the landscape that I'm working with, and I know that it's good to move along certain directions faster than other ones, or different things like that. Or maybe your algorithm can figure that out automatically based on the previous gradient steps that it's taken. So there are these types of what we call adaptive algorithms that might tune the learning rate in different ways along every single dimension that it's working with. We won't talk about that in this class, though. It gets a little bit hairier. Yeah. No worries. You can also ask after class. Yeah. I didn't show you why logistic regression is convex. I might update this slide because I think that this is not exactly true. I should probably say something more like for strictly convex problems or strongly convex problems, if those terms mean anything to you. If they don't, that's okay. Like logistic regression plus regularization. Then we can show that we can find the parameters that minimize the loss. Because we already saw that for logistic regression, we actually won't, right? We'll just keep iterating forever, finding better and better parameters, right? I believe it is part of your next homework to show that regularized logistic regression is strongly convex. But I believe that that also doesn't answer your question about why that shows that we'll minimize the loss. I defer that question to classes like 127 and 227, which can actually answer that in a lot more detail. Yes? Yeah.
I get like the adaptive learning stuff where you're like changing how much alpha changes by, but wouldn't just alpha being like a vector or matrix kind of defeat the purpose of the gradient portion of the gradient descent, where it's like this is the direction we're heading, this is how much we're changing because of the gradient?
Yeah, so that's a really interesting question about so the gradient is telling you both sign and magnitude direction, or magnitude information, right? Like in some sense, it's not just telling you which way to go, it's telling you how far to move as well, right? There are good reasons for certain hard problems like neural networks to not trust the magnitude information as much. Like if your loss landscape looks like really weird, right? Then maybe your gradient is telling you like move really far, right? Because it's really steep or something like that. But actually what you have is like something that like goes straight up like as soon as you leave that local region. And if that happens, then you shouldn't have listened to that magnitude information in the first place, right? It's not going to happen that much for problems like logistic regression, but for certain harder problems, it turns out, at least empirically, to be the case that listening to that magnitude information or trusting it too much can actually be a bad idea. Let's conclude today by talking about a slightly different topic, which is sort of extension of what we've done so far into multi-class classification. So far, we've only done binary classification, right? K equals 2. Every single yi that I have, it's either 0 or 1, right? But many classification problems are not binary. Instead, there are k possible classes where k is greater than 2, right? And then each label that I have, each yi, takes on some value between 0 to k minus 1. For example, if I have the digit recognition problem, which you remember I alluded to in the first lecture, right, then k equals 10, because I have 10 different digits that I'm trying to distinguish from 0 to 9, right? Here's some examples of people writing digits. And then for each one of these data points, we're trying to figure out what label, what class should I assign for this handwritten digit, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The k equals 10, right? There's 10 different labels that I might choose from. So things here start to get a little bit more complicated. But as it turns out, it's actually not super complicated either. And so we're going to look specifically at logistic regression and how we would extend it from binary classification to multi-class classification. So how do we rework our logistic regression model to handle k greater than 2 classes? Okay, remember what we did before is we had our model output a single number, right, theta transpose x. We pass that through a sigmoid. We specify that that's probability of 1, and then probability of 0 is automatically given as 1 minus that, right? So things were simple before. Things are going to be slightly less simple now, but it's not going to be that complicated either. So let me ask, theta, right? What was theta for our logistic regression binary classification case? Or just tell me, what was the dimension of theta? Yes? Yeah, it was a d-dimensional vector, right, that we just dotted with our x in order to produce a single number, right? What we're going to do now is we're going to make our parameters theta a k by d matrix, where d is still the dimensionality of x, but k is the number of classes that we have, okay? This something might look a little off here because for k equals 2, we had a 1 by d vector, right? So why didn't we have a 2 by d vector? Well, it's because we didn't need that. Some information is redundant, right? So technically speaking, I could make theta here a k minus 1 by d dimensional matrix, and everything would still check out because the last probability is specified as 1 minus all the previous ones, right? But just for simplicity, we're not going to do that. We're just going to say that theta is a k by d matrix. Then, if I take theta transpose x, nope. Theta is a d by k matrix, right, because I want to transpose it. So this should say d by k, right? Because then theta transpose is going to be k by d, which is what I was hoping for. So theta transpose x, for this case, for a d by k matrix, theta, is going to be a k-dimensional vector, right? 1 for each class. But we still are getting out these unconstrained real numbers. It's just a matrix vector product at this point, right? So what do we have? Oh, there we go. So we now have k unconstrained real numbers, right? But what we want are probabilities, right? We want the probability of this data point x belonging to each class. So what we're going to do is we're going to transform our outputs yet again, this time into k numbers, all of which are between 0 and 1, and all of which together sum to 1. Okay? Then we'll have each number representing the probability of the kth class for that data point x. Okay? So this is sort of just like a generalization of what we've done before. We still have this general idea of we have unconstrained real numbers, and then we transform them into probabilities, right? That's the basic recipe that we're still following here. So how do we actually output these probabilities? How do we make our model output numbers between 0 and 1 that sum to 1? So remember, we have theta transpose x, right? So this outputs k unconstrained real numbers. What we're going to do is we're going to make all of these numbers positive and then normalize. So we're going to divide by the sum of all of the numbers. And what this is going to do is it's going to make all the numbers fall in the range 0 to 1, and then they're all going to sum to 1, just by definition of what we're doing here, right? There are a lot of ways to make some number z positive. Z is here is just a placeholder, right? It's just, what do we do to z, an unconstrained real number, in order to make it positive? Well, in this context, the most common choice is the exponentiation function. So I'll do exp of z. This is actually very reminiscent of the sigmoid that we've already seen, right? So we're going to choose exp of z in order to make that number positive. And there are a lot of other choices. You could choose other things, but basically everyone uses exponentiation. So that's the one that we're going to stick with in this class. Okay, stick with me. So give me 1 minute, and I'm going to write out what it is that we're actually doing to transform real numbers into probabilities. It's what we call a softmax function. So the softmax you can almost think of as a multivariate generalization of the sigmoid, where the softmax of my model output, okay, is a vector, right? A vector of, k entries between 0 and 1 that all sum to 1. And if I'm just looking at the cth index of this output, okay, c between 1 to k, what I get is, remember, I'm exponentiating all of my model outputs, right? So I exponentiate the cth number that my model outputs, and then I divide by the sum of all these numbers. Okay, sum from I equals 1 to k, right, of the exponent of my model output. And then I use this to define